I'd like to work problem number 24 on page 97, and it looks pretty tricky to me. Now bear in mind there's one other topic in this section we haven't looked at yet. That's the Bernoulli form. And let me get the exact wording on that. It's the Bernoulli equation, lesson 11D. Haven't done that yet, but those would be problems in which you have a power of y. For example, number 23 has a y cubed in it. That's a Bernoulli equation. So we'll do those next. But this is an integrating factor problem. And it looked very interesting to me because if we did the normal thing, notice that it's written in differential form. And if I go to put it in derivative form, divide by dx. If I divide everything by dx, I've got x minus sine y, y prime, plus tangent y equals to 0. And so if to get the y prime by itself, we have to divide by this term here. So we have y prime plus tangent y over x minus sine y equals to 0. And we have something that doesn't look familiar that we could solve. Because remember, the problems we're looking at for the integrating factors are this form here, y prime plus p of x y equals to q of x. And there's our issue. We don't have a y coming out of here at all. So I'm thinking this method doesn't work. Okay? Unless, what if we do this? What if instead of getting y prime dy over dx, maybe we should divide by dy and get x prime dx over dy? Let's try that. And I believe it works. So I'm going to take a different approach here, a little bit different looking approach. And I'm going to divide this equation by, what did I say, dy. Alright, so let's see what happens here. I have, this cancels. I have x minus sine y plus tangent y dx over dy equals to 0. Alright, now I can divide by tangent y because I want the derivative by itself. And so now over here I have x over tangent y minus, and sine over tangent, sine y over tangent y. Remember that sine, that tangent is sine divided by cosine. So if we divide these, invert and multiply, the sines will cancel, and we'll end up with cosine. So, sine divided by tangent gives you cosine, doesn't it? Alright, so this will be cosine y plus the tangent y cancels here, and we'll call it x prime equals to 0. Well, now, is that a integrating factor type of problem? Well, let's see. If I separate this, I have x prime plus 1 over tangent. Now 1 over tangent is cotangent, so I have cotangent y times x. And then I'm going to bring this to the right side, the y term only goes to the right side, equals to cosine y. So if you think about this, this is the form, the first order linear equations of first order, as a book terms it, that allows us to do an integrating factor. And in fact, what I have actually is dx dy plus p of y times x equals q of y. So, in other words, the x's and y's roles are switched here. And as long as we have that in our head that, okay, x's and y's are switched, then we're going to be okay. We can solve this problem. So it does fit the integrating factor form because we have the derivative, we have the variable, and then the function of the other variable, Alright, so what's our integrating factor? Our integrating factor would be e to the integral of the cotangent y dy. And I'm going to look that up. Hang on. I don't have quite all these integrals in my head, so I just want to make sure. The integral of the cotangent function is the natural log of the sine. So this is e to the natural log of the sine function. And as you can see, the e and the natural log will cancel one another. So an integrating factor is simply the sine of y. And as usual, when you do this, the absolute value sign goes away. So integrating factor is sine y. Well, I need to work with this equation multiplied by the integrating, no, I'm sorry, this equation multiplied by the integrating factor. So I'm going to do a little erasing. I took our integrating factor, sine y, multiplied this equation. So I have sine y times x prime plus sine y times cotangent y times x equals sine y times cosine y. Right, well, these cotangent is cosine over sine. That's cosine over sine. So when I multiply by sine, the sines cancel, leaving cosine. So I end up with sine y times x prime plus cosine y times x equals to sine y cosine y. Alright, so I'm going to erase this stuff down here and then we'll try to wrap up this problem. So let's check. The left side, after we multiply by the integrating factor, should be the derivative of the integrating factor times our dependent variable x. So if I take this derivative with respect to y, I get x prime dx dy times sine y plus this derivative is cosine times x. So it works out. And multiply through by dy, I've got the differential of x sine y equals to sine y cosine y dy. Alright. So now we can integrate both sides. And the left side is just going to kill off the differential. So we have x sine y equals to, now the right side, we can integrate this by substitution, but also you might remember an identity here. The 2 times sine y cosine y is the sine of 2y. That's the double angle formula. So actually this would be 1/2 sine 2y dy. Isn't that nice? So again, let me go through that. The sine of 2y is sine times 2 times sine times cosine. The 2 cancels the 1/2. So in other words, we can just go right to here and integrate this this one right here. So what would that integrate to? If we integrate sine, we get negative cosine, don't we? Yes, we do. We get negative cosine. So this will be 1/2 times negative cosine 2y, but we're also going to be divided by 2. So let me go through that. Kind of in your head. If you look at this right here, ignore the 1/2. I put the 1/2 over this 1/2 right there. If I take this derivative, derivative of cosine is minus sine. So that's the 2 negatives cancel. I have sine 2y. The chain rule means the derivative of 2 times y is 2. I need that 2 to cancel. So we end up with x sine y equals to negative cosine 2y over 4. There we go. And so at this point, let's plug in our initial conditions. Oh, I forgot my plus c, didn't I? Plus c. Okay. Well, in that case, because we integrate, we need a additive constant somewhere. Got our plus c in. In that case, let me go ahead and multiply this equation by 4 to get rid of this. And I'm going to bring this term to the left also. So I have 4x sine y This comes over, the 4 cancel, this comes over as a positive, so it'll be plus cosine 2y. And 4 times a constant is still a constant. Alright, so that's maybe a little bit more convenient form for that answer. So this would be the answer to the problem if we did not have initial conditions. That would be a general solution. But the particular solution with this initial condition says that when x equals to 1, then y equals to pi over 6. So I'll plug those numbers in. 4 times 1 sine pi over 6 plus cosine 2 times pi over 6 is pi over 3. Cosine pi over 3 equals to a constant. The sine of pi over 6 is 1/2. The cosine of pi over 3 is 1/2. So I have 4 times 1/2 is 2 plus 1/2 equals to c. So c is equal to 5/2, isn't it? Alright, so my answer then, I can replace this with 5/2 equals to 5/2, and that should be the answer. Sorry, that's a little cluttered there, but I'll block it off with a rectangle. Alright, well here's the moment of truth. Let's see if we match the book answer on this. Number 24. Alright, 24, he multiplied both sides by 2. We got 8x sine y plus, oh boy, 4 sine squared y equals plus 3. Alright, so do we have the same answer as the textbook? Alright, let's see if we can reconcile the two. So we're trying to see if our answer matches the textbook answer. And I used an identity for the double angle identity for cosine 2y. One of those identities is 1 minus 2 times sine squared y. So I'll replace this with 1 minus 2 sine squared y. And if we subtract the 1 from both sides, 5/2 minus 1 is 3/2. So I end up with 4x sine y minus 2 sine squared y equals to 3/2. And now let's multiply by 2. And I think it's going to work out. Thank goodness. I'll work down here to wrap this up. We'll get 8x sine y. And then my multiply here I get minus 4. I'm going to add this to the other side. And so I end up with 4, positive 4 on the right side, sine squared y plus 3. So let's see if that did it. And they have 8x sine y equals to 4 sine squared y plus 3. So big sigh of relief, we matched the book answer. So